Welcome to Energy Talks, a regular podcast series of expert discussions on power system testing topics. My name is Stefan from the podcast team at OMICRON, and I will be your host. Hello everyone, this is the first episode of our new mini-series called Circuit Breaker Testing Around the World. We want to have expert discussions about what circuit breaker technologies are used, how circuit breakers are tested, and the reasons for these differences all over the world. My name is Stefan, I work at the OMICRON headquarters in Klaus, Austria, and I've spent about 6 years focusing on circuit breaker testing all around Europe. In this first episode, I have the honor of talking to Charles Sweetser from North America. He has experience in testing all kinds of assets for many years and is talking to me today from his home office near Portland, Maine. Hello, Charles, and thank you for taking the time to do this podcast today.
Yes. Hi, Stefan. Thank you. I'm glad to be here.
Awesome. So let's start with talking about you a little bit first. So what's your background? How long have you been in the business of testing power assets or primary assets?
Yeah, I've been involved in testing for about 25 years, and I joined OMICRON back in 2009. And I work here in North America, both in the US and Canada, supporting apparatus testing of all different devices, transformers, and circuit breakers and instrument transformers.
But mostly focused on the East Coast, or are you going to the West Coast as well?
No, we focus on all of North America, both the US and Canada.
Okay, perfect. So before we go into circuit breakers specifically, what's the specific requirements that makes the United States or North America in general unique compared to other parts of the world?
If you look at it specifically, I don't want to jump into circuit breakers, but the circuit breakers in North America, a lot of the technology over the years, looking at legacy breakers, have really moved towards dead tank technology. And back in the years past, we used to use a lot of air blast and oil circuit breakers in transmission substations. And through, say, the past few decades, it's all have moved to dead tank technology using SF6 for the higher voltages. And for the lower voltages, a lot of vacuum technology is used.
Okay, so I guess we're right in the middle of it, because whenever in Europe, if we talk about circuit breakers and we talk about North America, dead tank is the big issue. So let me just get straight to it. Why does North America use dead tank circuit breakers?
I think with dead tank, whether you use live tank or dead tank, I think it's truly a preference, and it's hard to say really if one technology is better than the other. Again, it comes down to preference. For us, the benefit is being able to use the CTs within the bushing at a very low potential. Those phase CTs are in the bushing, unlike live tank breakers where a freestanding CT is required. However, we also use SF6 gas, which we can talk about that later, but there's a lot of changes now happening in the SF6 world. As we know, it's a greenhouse gas.
So you're saying it's mostly just a preference, but do you know why people in America prefer dead tanks? Because in Europe, I don't think I've ever seen any dead tank breakers whatsoever.
I just think it's a preference of evolution of how it was brought to be. I think the footprint is smaller for dead tank over live tank in substations. And then again, there could also be just a safety argument noting that these apparatus are fully grounded.
Okay, so you think it's mostly just historically that it was kind of used back in the days and it kind of just never changed.
Sure.
And so mostly you're
it's
still
almost an evolution of an oil circuit breaker, right? That is a dead tank circuit breaker. It's the same setup, similar footprint, same type of grounding potential.
Okay, understood. So with dead tank circuit breakers, we're mostly talking about the high voltage area, I assume. What is mostly used in medium voltage areas?
For high voltage, it's SF6 to basically anything greater than 72.5 kV. We see a lot of SF6. Below that, we see a lot of vacuum breakers being used. And there is a competition between technologies now. Vacuum is slowly moving into some of the higher voltages up into the 72.5 kV range. And everyone is really striving to get to 145 kV with vacuum breakers. And there's also a whole set of these new non-SF6 alternatives coming out that have more environmentally friendly gas associated with them.
Yes, so that was going to be the next question, like how is the trend evolving? So in high voltage area, you're still focusing on dead tank type breakers, I assume, but just going into different types of gases in that case.
Well, I think the race is right now, if you just look at the news that's available, really everyone is kind of shooting for 145 kV technology. And there is kind of a race between vacuum and non-SF6 alternatives, or I could call them fluorinated alternative gas breakers. So there's a little bit of a competition going there, but those breakers haven't really got to the high voltage arena yet. But that's really where these breakers are heading now.
Interesting. So we have basically very different trends in Europe because we're also trying to get higher voltages for vacuum type circuit breakers. We also try to get away from SF6 circuit breakers. We just use a different tank type in that case, which is, interesting that we have similar trends, but just in different types of circuit breakers. Mm-hmm. So when we talk about circuit breaker testing, what are in America like the essential tests for the condition assessment in circuit breakers? If we go talk about medium voltage and high voltage, maybe.
All right, so I think, we've always tested circuit breakers. We do break it down into different components. So I just want to be clear that normally we can do insulation integrity tests, and then we can do performance checks, and I can speak a little bit about that. But in terms of insulation integrity, we could do power factor and capacitance, we could do partial discharge, we could do insulation resistance, withstand test. And depending on what type of breaker it is, if it's an older oil breaker, we can do DGA and oil screen. And for the more modern SF6 breakers, we can do SF6 quality, which would include moisture, density, and some SF6 byproducts could be tested. But in terms of performance testing, of course, we can do timing tests. We can do open and close timing. We can do trip-free. We can do reclose timing. We can look at the mechanism, and we can look at the physical properties such as total travel, zone velocity, over travel rebound, and contact wipe are just a few of the tests that we might do. And then, of course, we do look, it's not in the same area, but there are CTs associated with breakers. And of course, we can do CT tests on those CTs. And then some other tests that come out. There's another test called first trip that's done often in North America, looking at a circuit breaker that hasn't been operated in a while and capturing that first trip as an example.
Very interesting. Since you use dead tank breakers, you have the whole insulation tests that we normally don't do as much here since we have the live tank breakers. But if you talk about the performance, it seems very similar to what we performed. There was quite a long list of tests. If you only have let's say 30 minutes to test a breaker, what are the absolute essentials where you get the most information out of very little time?
Probably if you have a breaker out of service and we want to look at the tests, I would probably go for timing, open and close timing, again, trip-free, reclose timing. And if the equipment's available, of course, we can do motion measurements to include velocity and travel and all of those measurements associated with it. So usually the performance check is good, but it all depends on the policies of the asset owner, because there's a lot of subjective opinions about insulation integrity, especially in SF6 breakers. For commissioning and acceptance testing, power factor is pretty much always done, but for routine testing, these breakers have been so reliable through history that people often don't perform power factor, as an example, on an SF6 breaker that's been in service. However, though, you do probably want to check the SF6 gas and really check it for moisture and density.
Interesting. So for you, the basic test is still timing test. That's the most essential one. What I wanted to double check, you said the trip-free test, which is not a phrase we use in Europe. Can you quickly explain what that is?
It's basically a close-open test.
Oh, okay.
Well, we're going to close the breaker, but then immediately within milliseconds, issue a trip command and see how fast it takes for that circuit breaker to return. Does it go completely to close, and then does it return back? And does it do it within a specified time?
Okay. So it's basically simulating turning the line on onto a fault and then immediately turning it back off to avoid any harm. So you said in North America, you have the conversation about the importance of the insulation testing. Basically, we have a similar conversation here about the vacuum models in medium voltage. Is that also something that you perform? What are your opinions on testing the insulation of the vacuum breakers?
Okay, well, vacuum breakers, this may change because we're moving into higher voltages, but for the most part, the vacuum breakers were applied to basically lower voltage switchgear, a lot of vacuum breakers in cubicles. And often a power factor test would not be performed. What is really recommended is a vacuum bottle test done at a higher voltage to really check the integrity of the vacuum bottle in the open position. So to a certain degree, there could be some insulation resistance tests on that vacuum breaker, looking at some of the terminals to ground from that point of view. Yeah. But for the vacuum bottles itself, it's usually a higher voltage withstand test that's performed on the vacuum bottles.
And so do you regularly perform those in a routine test?
I wouldn't say all the time in a routine test, but maybe after a certain time period, it's possible, yes. You might want to perform the vacuum bottle integrity test. You probably would definitely perform the insulation resistance tests.
Okay, interesting. So in high voltage, you recommend doing the insulation tests for the higher voltage breakers. For the vacuum, it depends, and maybe not as regularly, but after a long while maybe as well.
But again, in the higher voltage technologies, it's still a little subjective whether people perform power factor on these higher voltage SF6 breakers.
Yeah.
It's because of their proven track record. However, though, we do find problems. There's no question we do find problems with power factor on some of these breakers.
Okay, so speaking of high voltage circuit breakers.
High voltage breakers.
Okay. So if you go to a breaker, you want to do not just the simple test, but a full test. How do you go about testing? Let's focus on high voltage, so on a dead tank circuit breaker. What makes it unique? How do you have to test a dead tank circuit breaker in order to get a full picture of its condition?
I think that when we look at breakers, whether they're just dead tank, right? We have insulation systems. What is the arc extinction method of that breaker? What is the mechanism? What sort of contacts are they using? Because we know that the contact system from a vacuum breaker is a completely different technology than what's used in a nozzle system in an SF6 breaker. And of course, we have control circuits that could be somewhat different. But for the most part in North America, regardless of the breaker, these apparatus are very similar, right? Our problem here in North America is basically installing a travel transducer on the breaker. This is one of the most difficult things. Some breakers are easier than others. Some breakers you can use a rotary transducer. Some breakers are going to require a linear transducer. But the difficult part is sometimes when you apply this transducer, you need an adapter. Maybe that adapter is not available. And the other thing is the location or the spot where you mount this transducer might not be a direct link to the movement of the contacts. So there could be some sort of conversion needed to get us from that movement of the transducer to the actual movement of the contacts on the breaker. Because it's tough. If you go back several decades when we were using oil circuit breakers, we would install a rod right down onto the contact assembly itself. The rod would actually attach and screw right into the contact assembly. So when that rod moved, it was a direct translation of the contacts. And the measurements were more basic in that fact. But today, a lot more has to be put into it, and a lot more thought and design has to be put into it to really measure and properly install these transducers. So even with dead tank breakers, to me, are really difficult. It's not always easy to find that direct translation or the best translation to the main contacts.
Interesting. So in this case, the older times really were simpler and you could just measure it directly. Let's maybe switch it up again to the most basic motion measurement you could do. What is like the quick and dirty type of measurement where you just get like a simple, at least quick look at the motion of a breaker? And what would be like the ideal scenario where you get the whole picture of the motion measurement?
I don't think it's a quick solution. I think what it comes down to is you need to basically measure it as it was measured in the factory. Often the instruction manual will detail how they perform the measurement. And even if that measurement isn't exactly to what the contacts are doing, as long as you repeat the way the factory did it, the factory is going to list all of the performance limits.
Yeah.
And from there, if you perform that measurement the same way, and we compare the millimeters of travel, we compare the zone velocities within limits, and some of the timing, and normal trip time could be around 26 milliseconds as an example, but there'll be a lower and a higher limit to that. And what we're looking to do, unlike power factor testing, which can be subjective, you can look at the values and have different opinions, with circuit breaker testing, if it's tested, the value should be within these manufacturers' documented limits. So the key is to set it up correctly, be confident with your measurement, and perform the measurements and fall within these specifications.
Interesting. So you're not really trying to do like a perfect measurement or a basic measurement. You just want to do it as closely as possible to the initial measurement that was done at the factory, so you can compare the values as good as possible.
Correct. And sometimes the factory will also document conversion factors in that instruction manual. And you need to read carefully, make sure you understand that if there is a conversion factor, that you put that into your measurement so you can compare to those factory specifications.
Okay, good to know. So for any customer or anybody testing circuit breakers and they've never done any motion measurements whatsoever, what would be your advice, first of all, how to start doing that, or maybe why they should do it? Like what kind of value is missing if they don't perform this type of measurement?
Sure. I think if you're a new customer, I really think to a certain degree, you have to obtain some training. And I think what's important here is a concept training, not a specific training on specific breakers all of the time, but understanding the different types of transducers, whether it's rotary, whether it's linear. All new modern transducers are digital, which is good, but you could have a digital transducer, you could have an analog transducer, and really understanding how to interpret and read the instruction manual so that you can apply these measurements. I think the other measurements are pretty straightforward. If we're going to do close timing, open timing, reclose, trip free, as I talked before, I think that's pretty straightforward. That's just a stopwatch. All modern instruments do a very, very good job on this. I think the hard part is incorporating the motion measurement into your process.
But you would say, is it worth it to have this additional effort, which we now talked about, how complicated it is in some cases to really get accurate measurements? Is this something somebody should do that wants to test circuit breakers?
I want to say that there's a limit, but for higher voltage circuit breakers, 72.5 kV and above, I'm a very big supporter of the motion measurement.
Okay.
And it does add a level of difficulty, but I think it's important because it really lets you know how fast is that breaker really moving in this, what I call the arcing zone. Is it moving at the correct velocity recommended by the manufacturer?
Okay. So one test, maybe I've missed it, but I think we've not talked about it all yet, is just the contact resistance. So is this something you perform regularly or less in America?
I would say the contact resistance test to me is really required. As a required test, I think it's quite easy. It's not a test that's going to take a lot of time. And if your breaker is out of service, it's very easy to apply. But again, the manufacturer is going to put limits. And for most dead tank SF6 technologies, we're kind of looking for anywhere between, say, 100 microohms up to maybe 150 microohms. But for some vacuum breakers, we want to see much lower values. I mean, and sometimes I like to see vacuum breakers as low as 25 microohms. These aren't limits. You really have to go by the manufacturer's recommended limits. But this is going to really give you an indication if there's any obvious failure mode or anything going on with the contact itself. So this measurement is quite important. And again, but it's quite easy to do. And you just have to make sure your connections, that you do things properly, because we're measuring such low values. You need to really have the test set up right, and you'll get good values. And of course, we're going to apply a 4-wire measurement Kelvin connection for values this low. And you just need to know basically what's involved with the Kelvin connection. And the measurement is pretty straightforward.
I think I've even seen vacuum breakers with the range of like 16 to 18 microohms. So yes, you can go very low there. From a European perspective, we're always a little bit maybe worried, maybe even scared of potentially testing dead tank circuit breakers because of the CT effects, especially on the contact resistance. So how do you go about avoiding the CTs having any effects on your measurement results?
Sure. The CTs really affect almost all of the measurements to a certain degree, just because of the inductive effects of the CT want to basically oppose a change in any signal or current flowing through the breaker. So when we talk specifically about the contact resistance test, we often have to apply the injected current for a much longer time period, usually up to about 30 seconds. So this isn't an immediate measurement. With my experience looking at and actually measuring the waveforms to really determine the time, it really takes close to 20 seconds to basically get the DC get the CT saturated and get this DC current to stabilize. So we like to pick a minimum of 30 seconds. Some people use as much as 60 seconds current. And also keep in mind, I don't want to change the subject, but when you start to inject current into these circuit breakers, those CTs could still be connected to your relay system, to your protection system. And you want to make sure you have a process in place where you don't have a nuisance trip of the system. That wouldn't be something that's very favorable. So that should be considered. We do have different ways of trying to control the current so that this doesn't happen. Methods of ramping the current instead of going from 0 to 100 amps through a step. We can try to ramp it to try to minimize anything that could happen on the protection system. And of course, you could just set your protection system into maintenance mode, and that would also correct the situation. But again, it's hard to make recommendations on that because for all the end users, it's really their policy on how they want to set up the process to test the breaker. But regardless, this contact resistance measurement is really required.
Okay, but you're saying there's no reason to be scared. It's just about a 30-second extra effort. What kind of currents do you use in order to make sure that those are saturated?
There's not a lot of direct standards or guides, but basically 100 amps is what is really practiced here. And that's for all breakers, whether it's a dead tank SF6 or vacuum breaker. We try to inject 100 amp through the contacts because that also helps. The higher the current, it will give us a little bit better of a voltage drop across the contacts for measurement purposes. And remember, we're going to be in the very low micro to millivolts for a measurement. And that's not always an easy process in an environment that could have interference from adjacent equipment.
Okay, so all you need to test the dead tank circuit breaker, if you don't have any prior experience, is a little bit more time. You need a little longer currents. I think all those the cables have to be longer, right? Because you have to have these 100 amps really for 30 seconds right at the top of the bushings. Is there anything else that, let's say, a European would have to know in order to go test a dead tank circuit breaker?
Again, I really feel that if you look at a circuit breaker and you define it, there are a lot of common attributes that we're dealing with in our control circuits, regardless of the end user, whether it's a utility or an industrial customer, and even regardless of manufacturer, the terminal blocks are wired in a similar fashion. So we talk a lot about terminals 1 and 2. We talk a lot about terminals 5, 7, and 9. That's just terminology in North America. I can't guarantee it's always that way, but it's very, very common. So taking a look at the wiring diagram, we can see those points. So whether it's even a vacuum breaker or whether it's even a dead tank breaker, SF6 dead tank breaker, or an old oil circuit breaker, a lot of these points are the same. Depending on the mechanism type, whether it's a spring type or hydraulic or pneumatic or magnetic actuator, how is the system charged? And we see a lot of spring type breakers here that have motors, and some of these motors have backups. These motors can be operated in either DC or AC, and they need to be tested under both scenarios to make sure that the circuits are working properly. But we are seeing a lot of these new magnetic actuator breakers, specifically in the vacuum area, being widely used now. And again, it's still similar to what we're doing. You just need to be aware of really what you're testing. So I don't think you need to be that worried all of the time. I just think you need to have a little bit of training and most of all experience. You need to go out and basically take the time, test a few breakers, and I really believe that the confidence of the person performing the tests will improve and increase significantly just after a few tests.
Yes, I can confirm that. The first few circuit breaker tests in my life have always been, you're just overwhelmed with all of it. But after a few times, you see the similarities in even different types of breakers, same way as you said it. Even though I have to say in Europe, we usually don't have the same terminals for coils. We usually have to search them and they're all over the place. So that seems quite convenient that you usually have the same numbers for those. Okay, so maybe any last words for circuit breaker? Is there anything you still have on your mind that you would like to share that we haven't discussed so far?
Yeah, one good thing to be aware of is I really think that the technology, again, just to review, I think the technology is changing. To me, there's a competition now between vacuum circuit breakers and some of these new non-SF6 alternatives. And I think it's important for the climate change topic for this to happen sooner than later. And it's really happening. And I think for people working on circuit breakers and testing circuit breakers, really should try to follow this information and this news that's really coming out. And you'll hear terms now that are coming out, such gases, just as an example, a gas called G3. And you'll hear other terms like Novec and Air Plus. These are all technologies that are being now slowly introduced into the North American market. And I think that this is a very good thing for us. And it's going to require some changes on our behalf, but we're really going to have to see how these work and how these breakers are tested and basically learn the technologies, because I think it's something that's definitely happening as we speak.
Awesome. Thank you for that summary. Before we end it, I would like to ask you one last question, a little bit different. Since I have the opportunity to talk to grid experts now all over the world, especially in Europe, we have this conversation about potential blackouts now with energy crisis, etc. So I just wanted to ask one question. How do you see the general resilience of the power grid in North America at the moment?
Yeah, I think there's still work to be done in terms of modernizing the grid. I think we have a lot of effort right now going into digitizing the grid. And I think that there is also a little competition between distributive systems and bulk systems. I really think in North America, we need them both, but we really have to try to embrace changes and accept all of our renewable options that we can, of course, but at the same time, we still need to serve all of the customers and really produce a stable system and a secure system. And, there's all new topics as these systems evolve. Of course, cybersecurity is huge. We just had an event here in the US over the weekend regarding physical security of substations. And of course, that's also a very important thing in terms of protecting our grid. And of course, with all of the events over the past couple of years with the supply chain, we are seeing on the specific side, specifically for transformers, we're seeing really long lead times. And we need to make sure that we can safely manage that to really maintain a reliable, resilient, and secure electric power grid here in North America.
Awesome. So you see challenges ahead, but nothing that is not manageable.
Well, it's hard. These are all subjective opinions.
Yes.
And of course, and we never know where things are going to go, but I think a lot of effort is really being put in to manage this situation to meet our needs.
Thank you, Charles. That was amazing. Thank you for your time. Maybe we'll have another discussion at some point. Thank you for your inputs regarding this topic.
It was a pleasure. Thank you.
Thank you. We hope you enjoyed our conversation, and we want to thank you for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@OMICRONenergy.com. OMICRON has several years of experience in power system testing and offers you the matching solutions for your application. This includes devices for testing circuit breakers, which are the topic of this conversation. For more information, be sure to visit our website at OMICRONenergy.com, and please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.